Okay, so this is part 2 for the lecture for Monday, November 6th. We are continuing to talk about confidence intervals. So let me jump to R. Okay, so you're seeing where we left off with the review from last time. I'm currently in the bootstrap.r script, and as you see, it ends with that statement of if the sampling distribution is right skewed, then perhaps the confidence interval should be left skewed. I'm going to jump to a different script now. This is 2-1-bootstrap NP that's supposed to be non-parametric and parametric. So we're starting this new script, but we're going to skip the first bit of it. And the reason is that basically this script, much of the first half of this script was replaced by the bootstrap.r. So this script is going to go through non-parametric bootstrap and parametric bootstrap, etc. The example that is being used is finding the mean of a normal distribution. And so the reason that the bootstrap.r was written was to give a distribution with some right skew so that I could illustrate that reason for the pivot. So if you look at this script, you'll see that we're going to have a sample size of 50, we're going to have a mean of 3, we're going to have a standard deviation of 5, and we can sample from that normal with mean 3, standard deviation 5, and store our sample in Y. And then, so this would be like the sample we go out and collect, and then we estimate the mean of it and the standard deviation of our data. So our mean estimate is 3.5, the standard deviation estimate is 4.1. And then what's being done here in lines 20 is sampling from the true distribution. So this is that repeated sampling exercise, which if we knew the underlying distribution we could do, but of course in practice we don't. So in lines 38, we're going to do our non-parametric bootstrap. So you can see that we're creating this thing theta b where we're going to store our bootstrap means. We're going to do 5,000 bootstrap samples. Each bootstrap sample is going to resample from our data y. It's going to take the mean of that and store it. And so here we've done that bootstrapping, and here is the histogram of our bootstrap mean. So we see that it's centered at 3.5 rather than 3 because we're resampling from this sample y that had a sample mean of 3.5. And, you know, in this case, it's roughly symmetric because the underlying distribution, the normal, is symmetric. Here is doing parametric bootstrap. I'm going to skip that, but you can see that what is done is you estimate the mean and the sigma from your observed data, and then you repeatedly sample from the fitted distribution. Okay, so lines 85 is repeating our investigation of mean variance and bias. Here is the quantile method where they would just take the 0.025 quantile and 0.975 quantiles and get the confidence interval. Here, picking up at line 100 is where we do the basic bootstrap. So instead of taking the 0.25 quantile and 0.975 quantile from our bootstrap means, what we're going to do is we're going to take the difference between our bootstrap mean and the mean that we get from our original data. And so here is that. So Q now has 5,000 estimates. You can see that it's kind of basically what we've done is we've shifted that distribution so it's now centered at 0. The center of our bootstrapped means was at the estimate 3.5, so we've centered this thing. And then our confidence interval, what you see here, is we're going to take theta hat minus quantile, and you can see that our 0.975 appears in the lower bound, our 0.025 appears in the upper bound. And so this is just showing what the true distribution would be if we were able to illustrate from, if we were able to draw from the original distribution. The important thing is this here, where we got our confidence interval. The lower bound is 2.4, the upper bound is 4.6. We see that that covers the true mean of 3, which we think that this should cover that true mean about 95% of the time. Okay, so just jumping back now to the notes. We did exactly this. Our Q in the code took our bootstrap sample means, subtracted off the mean from our original sample, that 3.5. We created a distribution of that, so that was our centered distribution. We took the 0.975 quantile, that appeared in our lower bound. We took 0.025 quantile, that appeared in our upper bound, and that gave us our confidence interval. Okay, so so the next type of bootstrap is again going to be pivotal, but now we're going to introduce it's going to be basically like a T distribution. Now, so what's the difference? The difference is this quantity here. What we're going to introduce is an estimate of the standard error. So in what we were just doing, what we did from each of our bootstrap samples, we collected 5,000 bootstrap samples, a non-parametric bootstrap sample. We took the mean, we stored that mean, we did that 5,000 times. That was the histogram that we plotted. We know that when we collect a sample, we're of course going to, our mean estimate is not going to correspond with the true mean. And also the standard deviation of our estimate is not going to correspond with the true underlying standard deviation. And so that the fact that we estimate the standard deviation is important because we know that when we have to include an estimate of the standard deviation, even when the true distribution is normal, the right distribution of this is the T distribution because we've included that sample, that estimate of the standard deviation. So the next bootstrap tries to capture that idea. And so just like this would be the true T statistic. What we're going to do is we're going to get a bootstrapped statistic, which is going to take our mean estimate from our bootstrap sample, subtract off the mean estimate from our original sample, and it's going to divide by the standard error of our bootstrap sample. So the big difference here is that we're going to not only, for each of our bootstrap samples, we're not only going to store the mean, we're going to store a standard deviation. And then, just like we would get if we calculated a t-based confidence interval, what you would do is you would get the 0.025 quantile, the 0.975 quantile from the back of the book, or from the from QT in R. You would get those quantiles depending on the degrees of freedom, and you would plug those in. Well, what we're going to do is we're going to replace that looking up in the book where the true distribution is T. We're relaxing that assumption of underlying normality, and we're just going to use our bootstrap to calculate that. So we're going to calculate a whole bunch of these statistics. We're going to get the 0.025 quantile of these statistics, the 0.975 quantile of these statistics, and we're going to plug them in, 0.975 in the lower bound, 0.025 in the upper bound. So the as this says, this method generally provides confidence intervals with good coverage properties. The drawback of this is that this really can only kind of be done for means, because we know that the t distribution for the t is the right distribution for the means. Basically, we know how to adjust for this standard error. The other drawback would be we have to store not only our mean from each bootstrap sample, but the standard deviation. Okay, so let's jump back to R. Okay, so now, if you, let me see here. So let me go back. Okay, so up here under non-parametric bootstrap sample, this is not the T yet. I'm trying to illustrate the difference between this and the T. What we did was for each bootstrap, we stored the mean from each bootstrap sample, and that was all we did. So notice that the big difference here is when I do the studentized bootstrap, I'm going to get my bootstrap sample, I'm going to store the mean, but I'm also going to store the variance associated with that mean. And we know that, so I calculate the variance of my bootstrap sample, and I divide by n, because the variance of the mean estimate is less than the variance of the underlying data, right? If the variance of the mean estimate is the variance of the underlying data divided by n. So I'm going to run this. So I'm going to, so this lines 114 and 115 just create the objects to store our mean and standard errors in. I'm going to do 10,000 bootstrap samples, and again, storing both mean and variance. Okay, so we've collected those. Here, this corresponds with that fraction we saw in the notes. We take our bootstrap sample, we subtract off our bootstrap sample mean, we subtract off the mean from our original estimate, and we divide by the standard error associated with our estimate, which is the square root of the variance. So I get that collection of T stars. Here is our standard error associated with theta star, and then this is going to correspond with that line from the notes to get our confidence interval. Here is our confidence interval, 2.43 to 4.80. Notice that that is a little bit wider. We definitely particularly that upper number has increased a bit. And that basically that's trying to, that additional uncertainty is arising from accounting for that uncertainty associated with the standard error. So here is histogram, and this is because remember when we jumped to this new script, our true distribution that we were drawing from was a normal. And so the true sampling distribution, when we're estimating the standard error, is going to be a t. And what this is designed to show is that under this particular situation, this estimate of the sampling distribution, which accounts for the t, very closely mimics the true t distribution. Okay. So the double bootstrap is a method for, we know that when we're calculating the mean, the variance of the mean estimate is the variance of the underlying data divided by n. And so we use this n. But if we're doing something other than the mean, then we don't know that relationship. And the double bootstrap is designed to do that, to account for that. If you look in this for loop, here we're collecting our bootstrap sample, we're collecting our mean, and then what we do is another bootstrap. So we bootstrap this bootstrap to get and we do this a bunch of times to get the uncertainty or the associated with this estimate. And so that's just an illustration of the double bootstrap. So let me just return to the notes. Okay, so again, thinking about that t distribution, we created repeated draws from this, and then we created our confidence interval this way, and so that's accounting for the standard error. So next time we will talk about bootstrapping for regression. We'll also probably talk about bootstrapping for dependent data. Again, I apologize for not being in class and not being able to do the usual echo thing because I'm not in class, but hopefully this will be sufficient for today, and keeping my fingers crossed that I'll be back in class on Wednesday. All right, that's it for today.